Okay, hello everyone. My name is Xiong. I'm now a PhD candidate on Xiamen University. Today I'm very pleased to present our work, RosenBridge. It is a framework for enable express I/O paths across the virtualization boundary. Let's start with the motivation. Virtualization is the backbone of cloud computing. It's isolated the guest and the host to ensure cloud security. Today, CPU and memory virtualization are highly optimized with hardware assistance such as Intel VTX and EPT. They provide near bare metal performance. However, for storage, cloud vendors usually rely on software parallel virtualization like Virtualization. It uses a ring buffer for communication. It can provide essential but important cloud-native features such as over-provision, leave migration, and snapshots. But there is a heavy virtualization tax. Modern VM SSD such as Intel Optane or Enterprise PCIe 5 SSD are offering extremely microsecond latency. In such setting, the software stack overhead is huge. It may account for about 87% of read latency and consume massive CPU resources. To solve this, the industry introduced SPDK to use user-space drivers and pooling to reduce VM exits. However, busy pooling wastes CPU cycles when the I/O load is low, and worse, when the concurrence is high. It causes severe resource contention and performance degradation. Another solution is hardware assistance, such as SRIOV. It provides bare metal-like performance, but only a small number of specific hardware device support it. Furthermore, exclusive device assignment breaks critical features like leave migration and over-provision. So, is there any other solutions in a bare metal? In a bare metal environment, researchers found a highly effective way called near data processing, or so-called NDP. NDP pushes the computation logic down to the low-level driver, such as NVMe driver, and some cutting-edge works even offloads the logic directly inside the SSD, such as Lambda I/O. By processing data near the device, NDP completely avoids moving massive data through the kernel stack. Since NDP is so powerful, let's look at the core challenges of bringing it to the cloud. So can we simply adopt this NDP paradigm inside a virtual machine? The answer is the benefit is very limited because of the strict virtualization rule. The NDP logic can only be pushed to the guest virtual driver. The data still has to traverse through the heavy and complex host storage stack. And some NDP usually rely on real device drivers, such as GPU direct storage need to the raw PCIe bar memory to perform peer-to-peer memory DMA. But the PCI address in the virtual machine is remapped by the hypervisor. To break this wall, we designed RosenBridge. It allows guests to offload BPF-based NDP programs to the host safely. We have three goals. First, it maximizes the NDP performance. Second, make it transparent and easy to use. Third, guarantee host security and maintain QoS. And choose BPF because it provides cross-platform execution runtime and some basic security insurance, such as limited instruction runtime and memory access. To achieve this goal, we face four challenges. First, how do we cross the strict execution boundary? The guest and the host are completely isolated. And second, how do we support complex NDP workload patterns? Standard BPF is event-driven. It's very hard to support complex data-independent I/O resubmission tasks. And third, how do we program? How to, for example, how to map address when program run on both sides. The VM has an isolated view of memory and storage. This is creating a huge semantic gap. And finally, how do we ensure security? In a cloud environment, relying solely on the native BPF verifier is not enough to stop malicious attack. And next, let's see the system design of RosenBridge. Our system has three key components. First one is called volatile NDP. It's a new type of volatile device for closing the boundary. Second, an I/O ring-based scheduling engine to meet different NDP patterns. Third, a set of BPF functions for address mapping. To bridge the execution boundary, we extend the volatile protocol and introduce volatile NDP. It allows GIST application to safely offload the user space BPF code into host QMU user space sandbox. We achieve this in two main steps. First is the loading phase. When a GIST VM wants to offload a program, the front driver copies the BPF code into memory and constructs a custom volatile request. It specifically sets the type field and sends it to the host. The QMU backend receives this and loads the code into a sandbox using the UBPF interface, and returns a file describer or a BPF FD back to the GIST. On the invocation phase, when the application actually wants to perform I/O, it calls our newly provided read interface. The request carries the BPF program script along with the GIST metadata pointer once to the QMU backend. Once the QMU presses the request, it routes it to a dedicated work thread. This thread then actually triggers the corresponding UBPF using a specific file describer. Through these two steps, we successfully turn a standard virtual block device into a small computational storage device. And to meet a complex scheduling required by NDP workload, we integrate with the host I/O ring framework. We add hook points at both the submit and the complete stage, and provide three UBPF functions for BPF operates I/O ring. And through simple combinations, we can realize two usage model defined by SNI CSD specifications. It supports both direct usage, like database retrieval or flitter, and indirect usage. We call it on path processing, such as GPU direct storage and data compression. And to bridge the semantic gap between the GIST and the host, we provide a special BPF functions when the program runs on the host. This function securely translates the GIST virtual address into a host physical address, and this is totally transparent to the VM users. For security, our key insight is to execute the code in an unprivileged host Ring3 sandbox. We use the UBPF verifier to limit instructions, and the memory access is strictly limited to the GIST allocated bounds. We also reuse QMU's leak bucket to throw I/O and ensure fairness. And more details refer to this paper. And let us to look at two showcases. The first one is RosenBridge. The first one is Rosen XRP. XRP is a great work from OSDI 22 that resubmits I/O in the NVMe driver. But if we use the directly in a virtual machine, it only bypasses the GIST kernel. It still suffers from the host software overhead and NVMe seeds. With RosenBridge, we can offload the B tree or SN tree search logic down to the host low-level driver. And we use a volatile NDP bar memory to pass the virtual machine file system metadata to XRP on the host. Thus, the program can check results and resubmit the next I/O directly in the QMU, completely reduce the most of Vim access and virtualization overhead. The slide shows the evaluation results. Compared to the standard volatile block and SBDK, our RIS throughputs increased by over 400% and 100%. More importantly, the CPU consumption per operation dropped to less than 15%. This saves massive computing cost for cloud vendors. And our second showcase is Rosen GDS, GPU direct storages. It enables peer-to-peer data transfer between storage and GPU. Implementing GDS in a virtual machine is difficult because existing native solutions have to rely on a mechanism called polybuffer, and it needs remap address to real PCI bar address on a NVMe driver. While memory addresses are remapped in the VM, the GPU driver in virtual machine cannot get the real memory address. RosenBridge solved this problem. Rosen GDS offload the logical that find the mapping and remap address on the host, and rely QMU to get a real GPU PCI bar memory. This established a peer-to-peer DMA path for virtualization I/O and vGPU. At the base of the knowledge, we are the first work to successfully enable GDS between a volatile device and a virtual GPU in a virtual machine. And finally, GDS reduced the end-to-end latency by 27 to 56% because it completely bypasses the CPU memory copy on virtual machine. And CPU utilization is reduced by at least 35%. To conclude, I/O virtualization taxes are too high. RosenBridge solves this by allowing VM virtual machines to safely push down NDP programs to QMU. We achieved the massive performance gains for database and AI applications. In the future, we plan to integrate this framework with DPUs. Thank you so much for listening.